Next up, we have Dr.
Gianna Cauzzi,
who's going to tell us a little bit more about how scientists actually use the sun's magnetic field to understand what's going on, and especially why we're so excited about the solar eclipse and the sun's magnetic field.
My name is Gianna Cauzzi, and I am a visiting scientist here at the National Solar Observatory. Today, after the introduction that Claire gave on the solar magnetism, we're going to talk in a little more detail about the sun's magnetic fields, how we measure it, its structure, its influence on its environment. It would be a much more boring start to study if it didn't have this magnetic field. So how do we measure magnetic field at the surface of the sun? We cannot measure it directly, and so we use an indirect method, and we measure the effects that the magnetic field has on the production of light. So by looking at particular characteristics of the light that comes from magnetic regions, we can infer that there is a field, how strong it is, which direction it has, and so on. Like in much of astrophysics, solar physicists rely on the analysis of light to derive a whole lot of information about the solar structure. And this is, incidentally, why we keep building telescopes. That's because we want to analyze this light in better and better ways. There are other instances in astrophysics when we do things differently. For example, we can send a magnetometer up on satellite on the Earth, in the Earth atmosphere, and measure the magnetic field there, for example. Or we can send a lander to Mars and measure directly. But the bulk of astrophysics is still by measuring and analyzing the light emitted by the celestial bodies. So if we were to look at the sun, and remember always to protect your eyes with, for example, eclipse glasses, we would see like a ball of white light, at least something that our eyes interpret as white light. Now, if you were to use a rather simple instrument like a prism, you see that this light is actually decomposed in many, many colors that we often associate with the rainbow, for example. And already by looking at this decomposition of the solar light, what we call a spectrum, we can learn quite some interesting things about the sun and in general about other stars. By using some instruments that are just a little bit more sophisticated than the prism, however, we can continue this process of decomposition of the solar white light into colors, having what we call a better spectral resolution that allows us to see finer details in this spectrum. And when we do so, we actually realize that the spectrum of the sun is not continuous, that is, that there are gaps in some particular colors. We see this thing and we call them spectral lines. For historical reasons, really. They are gaps. There are places in the spectrum where there is much less light than there should be. And what are these spectral lines? What are these gaps in the color in the spectrum produced by the sun? And why do they occur where they occur? They are absorption of the solar light emitted by the photosphere by elements that are present in the atmosphere of the sun. The important thing to remember is that these spectral lines are like fingerprints. If you have a certain spectral line in your spectrum, you know that a certain element is present. Spectral lines are very, very effective tools. The presence of the lines tell us about the elements that are in the solar atmosphere, but also, if we look in a little more detail, their shape, their brightness or not brightness, their exact position tells us a lot about the physical conditions that are in the atmosphere, including the pressure, temperature, the velocity, the magnetic field. So now we finally get to how do we measure the magnetic fields of the solar surface. There are certain spectral lines, not all of them, that have a very convenient feature when they are produced in the presence of the magnetic field. And that is that instead of being a single line, there is like multiple components of this line. So we will find the spectral line a little weaker in the same position as we always see it, but then on both sides of it there will be other components of the same light. And this is clearly seen in some cases if you look at the spectra of certain lines when you look at the light coming from a sunspot, for example, like in the image that is shown here. And the convenient thing is that the distance between these multiple components of the line is proportional to the magnetic field. So not only we know that the field is there, but also we know how strong it is. In the case where the field is not so strong, these multiple components might be all blended together, so this trick that I just mentioned is not very easy to use. And so we also rely on another property of the light produced in the presence of magnetic field. That is that the light that comes to us is polarized. Polarized is a difficult word, but essentially it means you know that the light is a wave, is an electromagnetic wave. And like all waves, it oscillates. So the electric field of the light that reaches us, instead of oscillating in a random way, it oscillates along a very defined and preferential direction. This is polarization. So and by studying the presence of polarization, the amount of polarization, and the direction of polarization, we also derive a lot of information about the magnetic fields. Probably you've heard or used polarized glasses or polarized filters for your camera, that they operate in the same way. Sometimes outside the light that you receive is polarized. For example, in a hot summer days over a body of water, you have that big glare coming from the water, and that glare is polarized. And so you put on your glasses, and magically that glare disappears because those glasses are filtering out the polarized light. We do the opposite. We want to keep the information about the polarization. So now that we know how to measure the magnetic fields at the solar surface, let's look at them. If we look at the map of the magnetic field over the solar surface, for example, like in this image, they are usually represented as these black and white maps. You can see the solar disk, and you can see these big splotches of black and white. The color represents the polarity of the field, so it indicates the north and the south poles of the magnetic fields, where the lines come out and go back into the solar surface. And the intensity of the color of the black and white represents the strength of the field. Take a look at the corresponding intensity image in the photosphere. You immediately see that the strongest magnetic fields correspond to the presence of sunspots. Indeed, it is the presence of the strong fields that create the sunspot, because the field inhibits the transport of energy from the deeper portions of the interior of the sun, all those convective cells that were mentioned before. So that actually at the sunspots you have less energy than you have in the surrounding areas, and the sunspots are dark because they are colder than their surrounding. Colder doesn't mean cold. We're talking about 4,000, 5,000 degrees Celsius versus the 6,000 of the surrounding photosphere, but certainly enough to make us realize that they are emitting much less than the surrounding atmosphere, than the surrounding surface. If they were on their own in the sky, they would still glow very bright. They would just be a little more orange than the normal solar light that we are used to. The largest, strongest sunspots have fields of the order of several thousand of Gauss. That's how we measure them as a unit for magnetic fields. And just to give you a comparison, the global average field of the sun is of the order of 1 Gauss. So is the average field of Earth, which is actually of the order of 0.5 Gauss or so. And that might be curious, but one of the strong refrigerator magnets that you have at home, that would be of the order of a few tens of Gauss, just to give you an idea. It's interesting to look at magnetic maps when no activity is present, that is, no strong spots, no active regions, and so on. For example, this is an image of a few days ago when there is nothing on the sun. And if you look at the magnetic map, you still see a lot of magnetic field. Maybe not so strong, not so concentrated as in the case of high activity, but there is still a lot. You see all this salt and pepper into the magnetic maps. And this is something to remember, that the sun is a magnetic star, no matter in which phase of this cycle we are, but it remains a magnetic star. So we've learned already from Claire's explanation the basics of the mechanisms that create magnetic fields in the sun and how they emerge at the solar surface. And one thing that you might remember is that in particular phases of the solar cycle, there is a lot of active regions at the surface and a lot of magnetic structures that are very close together. So you can imagine that all of these structures, they do interact and influence each other in creating an overall magnetic field configuration, which is rather complex. And in fact, starting from our naive idea of the sun as a bar magnet, as a dipolar field, with its simple structure of two poles and the nice and smooth field lines that connect them, we can get situations that are very different than that in the reality. At solar minimum, we are sort of approaching this situation, and the global magnetic field of the sun it's got structure mostly concentrated around the equator, and the poles are characterized by a lot of open field lines that don't close in the immediate vicinity and on the solar surface. While at the solar maximum, the situation is completely different, and so you have all these magnetic structures touching and conditioning each other, and there is a lot of these closed magnetic structures. So after all this discussion about the field, how it is, how it's formed, how we measure it, and so on, why do we care about it, besides the fact that it is interesting, and we physicists like everything? The fact is that the presence of the magnetic field and its structure, its topology, sometimes we like to say, which means its configuration, its shape, really determines the presence of the outer solar atmosphere. You have heard several times the words chromosphere, the words corona. Actually, this is what you will see during the eclipse, the corona, right? These things would not exist and would not have the shape and the intensity that they have if the solar field were not present. So looking at emission from plasma, from ionized plasma, from free electrons, we can immediately use them as tracers of the magnetic field configuration. And what you can immediately see is that during the minimum eclipse, you have this rather simple configuration of the corona, with the bulk of the emission being around the equator, and things that become also rather long. While at the maximum activity, the corona during the eclipse is much more complex and also much more distributed all over the sun, also at the higher latitudes. So you might ask, but instead of using the plasma as a tracer of the magnetic field, why don't you measure it directly? You've told me how to measure it on the solar surface, right? Why don't you do it also in the corona, for example? That's an excellent question. The fact is that the field in the corona is much weaker than what we have at the surface, because the field strength diminishes with height rather fast. Measuring the field in the corona is much more difficult than it is in the photosphere, and in particular, we cannot immediately apply the techniques that have been described before of the measuring the multiple components of the spectral lines. And there are reasons for this, which is that the magnetic field itself is much weaker. We're talking about Gauss instead than thousands of Gauss, so you can imagine that the separation of these components is almost impossible to measure. And this is compounded with the fact that the coronal lines are very, very broad. This is a characteristic that depends on the actual temperature of the coronal environment. And so these components are essentially drowned inside the width of the spectral lines themselves. The National Solar Observatory is currently building a new telescope, a 4-meter solar telescope to be operated in Hawaii, which is called the Daniel K. Inouye Solar Telescope. And one of the major goals of this telescope is actually to study systematically the field in the solar corona. Why can DKIST measure the coronal fields? Well, there are several answers to that question. One is that the KIST has been designed to be a coronagraph. That is, to be able to look at the corona every day, minimizing the glare from the photosphere, because the corona itself is so much less bright, millions of times, than the actual photosphere brightness. So you understand that there is a big difficulty there. And the DKIST, with its optics, is trying to optimize observations of the corona. The other important characteristics is that the instrument, which is being built with the aim of measuring the coronal fields, will work in the infrared region of the spectrum, which is better in terms of accommodating these coronal conditions, because the scattered light, the glare, is much less in the infrared, and also there are a lot of interesting spectral lines that can be diagnostics of magnetic fields in this part of the spectrum. So we are now at the point where we can actually check the statement that magnetic fields are essential to create the outer solar atmosphere, the chromosphere, and the corona. And this can be done nicely by looking side by side magnetic maps that tell us where the strong magnetic fields are on the surface, and maps of emission in the chromosphere or the corona at different temperatures. Different colors correspond to different temperatures. And if we do so, it's like a photocopy. You see that wherever you have magnetic fields, in particular closed magnetic fields, strong magnetic fields, and so on, you have a very bright and hot corona. Why is this the case? This is still an active field of research in solar physics. We certainly have a good idea of how it works, but all the details still escape us. The idea is that the magnetic fields that emerge from the surface of the sun and then extend, higher up in the volume, act as portals, as conduits from energy that is freely available at the surface, in all these motions of convective elements, and somehow they can transport it higher up and eventually dissipate it there, creating a hot plasma. The corona, eventually, the extended corona will give rise to the solar wind, which is this flow of charged particles that come from the corona and expands in the interplanetary space. And eventually that will hit Earth. And luckily for us, it will hit our magnetosphere, because we do have a magnetosphere. You remember that the charged particles cannot cross magnetic field lines, and so they cannot come straight at us, but they have to move along the magnetic field lines. So the solar wind, if it penetrates the Earth's atmosphere, will do so at the poles. However, there could be very strong events, bouts of solar wind that can have effects that can modify our magnetosphere, can modify the density, for example, of the ionosphere, that will influence transmissions. It will change electric fields, especially near the poles, and this will influence the transmission grid of electricity, and so on and so forth. And also, from very strong events, there could be effects that influence the upper atmosphere where our astronauts are normally stationed. Finally, let's go back to the structure of the corona that we expect at the upcoming solar eclipse of August 21st. And keep your glasses handy. And since we are in a phase of minimum activity of the solar cycle, the corona that we expect to be able to see is it's got more simple structure, concentrated around the equator, and while the poles shouldn't show much. There will be prediction about this. Our colleagues are pretty good in taking the magnetic field of the surface over a certain amount of time and predict what the corona should look like that particular time. And so it will be interesting to see if that comes true.
So hopefully Gianna's great explanation will really help you to appreciate why scientists are so excited to understand the sun's magnetic field during the eclipse. We hope that you enjoyed our webcast today, and we hope that you'll continue to join us over the next few months as we start to get closer and closer to the solar eclipse. If you have anything specific that you'd like us to talk about, if you have any questions you'd like us to answer, or if you just have suggestions in general, feel free to get in touch with us. You can find us on Twitter at @NatSolarObs. You can get us on Facebook at National Solar Observatory. And we now have an Instagram account at National Solar Observatory on Instagram.